Right.
Today, and recently he's been at Yahoo working on their very large-scale distributed systems, and we're lucky to have him here to tell us about ZooKeeper.
Great. All right. Thanks. I'm glad to be here. This is a great, you guys have a great department. You're very lucky. So I'm going to talk a little bit about ZooKeeper, a project that we've been working on for a couple of years. It's in production now. It's kind of a fun project. It's a talk I really like to give. Before I start the talk about ZooKeeper, I just wanted to give you a little bit of a view into what Yahoo Research Systems Group is like. We're a small group at Yahoo, and there's, I think, 6 of us now. We just got Tyson Condi from here. So we have a couple of projects we're working on. Now, inside of Yahoo Research, the systems group is quite small. Outside of Yahoo Research, it's large. I mean, we have huge systems. We have a lot of people working on really cool systems. So, also Flavio Junqueira is also from San Diego. So yeah, we have good representation. Yeah. So I just wanted to review. These are a couple of projects that I'm working on. Maybe Pig actually was my first project. It's a data flow language it's a high-level language for large MapReduce type batch systems. We're currently working on a project called Bookkeeper, which is a distributed write-ahead log. We have Hedwig doing pub/sub. There's a project we did with another student, Mo, from here, on overclock TCP. How do you tweak TCP parameters to get the best performance? And we actually made some really great discoveries for some of our front-end serving systems. We're working on a project called Inspector Gadget that will allow you to instrument, debug, and monitor large distributed systems. And then I'm going to talk about ZooKeeper. Now, of course, there's many others. We have scheduling projects going on. We have storage fabric projects going on with our partners, in production. So one of the things, just to relate it to a common buzzword of today, the cloud computing. Distributed systems have been around a long time. So cloud computing is really just another name for it. But of course, with these buzzwords come, different aspects that get emphasized. And so to me, I don't know if there's an authoritative definition, but to me, the 2 aspects of cloud computing that are most difficult and most compelling is elasticity. This idea that you have this big distributed system that grows and shrinks, right? That's one interesting aspect. And also the scale, just being able to use large number of servers. And so this work, the ZooKeeper work, is kind of targeted at that kind of a system. Oh, I wanted to find out. So is everybody systems here? Who can you raise your hands if you work in the systems area? Okay, almost everybody. Okay, good. Good. So I just wanted to put up a slide really quick on fallacies of distributed computing. I love this list of fallacies. Hopefully you guys have seen it. There's 2 reasons I love this list. One is because it's true, right? I mean, these are things that people think. This idea that the network is reliable. It's never reliable. That you always have some latency. And you have this list of fallacies. And the funny thing about it is you run into engineers that have been working a long time in industry that believe some of these things. I mean, it's just incredible. And actually, they've deployed large systems. It's incredible how you can believe some of these things and actually write a system, and it'll work for a long time. But these are some things you really need to keep in mind. And actually, I added one more. You know who's dead, right? There was this movie. Oh, I meant to ask what the name of it. There was this movie about I see dead people with Sixth Sense. Yeah. Sixth Sense, right? In that movie, you always think you know who's alive and who's dead, but that movie kind of teaches you otherwise. And in distributed systems, it's the same. I mean, even you're running a process and you look and you think you're alive and you may be dead. So this, even knowing who's alive and who's dead is a problem. Yeah. What, Sixth Sense? There you go. Yeah. Right. Yeah. So one of the things that you need to work on, that we need to deal with distributed computing is coordination, right? And so you can imagine we have, just like traffic, we have all these processes out there, and they need to coordinate amongst themselves. And if we don't, we run into traffic jams such as this one. So, of course, we know how to deal with that. We know semaphores, right? Semaphores are our coordination primitive. And so supposedly, I've never seen this, but there's an intersection in London that has these semaphores, right? And actually, I've seen pieces of code that look just like this, right? So coordination, you learn semaphores. It's very nice. You can teach it in a few minutes. But it takes, a whole career to master semaphores, right? So coordination is hard. It's important. It's hard. And so, at Yahoo, we have big systems. This is a picture of part of our data center. This is a portion of one of our Hadoop clusters. And we have lots of servers. It's so cool. I love working on lots of servers. You feel so powerful. I mean, I only work on infrastructure, so I don't know what to do with so many servers. But I still feel powerful. But so you have lots of servers, lots of data, lots of users. It's great. You have these interesting challenges like FLP, right? Being able to come to a consensus and cap, these trade-offs you have to make between partitionability and consistency. So you have all these interesting problems. And for a distributed computing researcher, it's great. It's such a great place to work. Now, if you're writing the next social app, it's a pain, right? It's really horrible to have to deal with these problems. So a lot of our work focuses on making it easier for the average programmer. Well, I shouldn't say average. The programmer that isn't a distributed computing scientist to be able to write code that runs on this large number of machines. And always keeping in mind that, programmers are mere mortals, right? We can always come up with some esoteric way of doing things, but we need to make it accessible for the mere mortal programmers. Okay, so what do we do? What does the programmer do? So this is one way, a very simple and reasonable way to deal with a large distributed system, right? You have a bunch of slaves, right? So a slave, there's many. This could be thousands of slaves. And they coordinate with each other by communicating to one process, the master, right? The master has a global view of the system. There's only one, so it has a perfect view. You don't have to worry about consensus because it's easy to get consensus with one person, right? So this is a great way to write a distributed system. And you see many distributed systems like this. GFS, Hadoop, MapReduce, the job tracker. So these all have this notion of a single master with slaves. Now, there's a couple of problems with this architecture, though. That this is a single point of failure. It's a scalability problem. It could be a bottleneck to performance. Also, there's something very tragic about this picture, and that is that the application developer, he's really interested in the logic that runs at the slaves, right? He's interested in application logic. He's not interested in building a reliable coordination service. So even in the cases where we've had one master, in the systems we've looked at, we find that these masters are often very neglected. So not only is it a single point of failure, but often it's a very unreliable single point of failure, simply because the application program is interested in working on its application and not the master code. So the next step you can do is if you have a coordination service, you can stick with the same master architecture, but then you can have a backup master, right? So if there's a failure, the slaves can connect to the new master. Now you need coordination so that you don't have two masters at once, and so that you can keep the system consistent, right? But this is kind of a nice bridge, right? So another kind of more distributed architecture is to still have the masters and backup master, but also have the slaves talk to the coordination system. Oftentimes we've seen in the previous architecture, the master still gets overwhelmed. As you scale up the number of slaves, it can overwhelm masters. So if you can coordinate through the coordination service and you have a nice scalable coordination service, then you can get around that problem. And of course, the coolest architecture is just to have workers that coordinate amongst themselves with the coordination service. That way you kind of remove some bottlenecks and single points of failure. So I've been kind of talking about coordination in the abstract. So let me just give you a couple of examples. They're by no means exhaustive, right, of what I mean when I say coordination. So one is group membership. Which processes are alive? Which processes can we communicate with? This also helps you answer the problem if you're alive, right? Are you a member of the group or are you not? We have leader election. In that second slide where we have a master and a backup, we need to make sure that at a given time, only one of those is active. Dynamic configuration is another big one. As your system gets big, when you change configuration, you don't want to restart systems. So oftentimes, when you have a system that runs on thousands of machines, it takes a long time to shut down and start up, right? So you don't want to have to shut down and start up a system every time you want to make a configuration change. So it'd be really great to be able to push out new configurations and just have them take effect dynamically. We have monitoring. There's queuing, barriers, critical sections. So these are all kind of what to think of when I talk about coordination. Oh, I should point out, if you guys haven't, this is a rather small group, so if you have any questions, please feel free to interrupt, okay? So some of our goals. This, of course, has been done in the past. There's a long history of solutions to these distributed computing problems. And we, of course, use a lot of them. I mean, or we certainly take notions from them. And we've learned from their trailblazing. So ISIS is one of my favorites, actually. It was a lot of the ideas are inspired from that work. We have distributed locks. We have Chubby is the recent one. VMS, the old system, had locks, distributed locks. So one of the things that we really wanted to focus on as far as goals is high performance. In our big systems, we wanted to make this system write it in such a way that our application programmers can use it extensively. So we didn't want to write something that could only be used for coarse-grained coordination because we just felt it was a shame to require our application developers to learn a whole new API and then only be able to use it a little bit, right? So we want really high performance. And so there's a couple of things we do to achieve that. One is we want multiple outstanding operations so we can get high throughput. And we also are targeting a read-dominant workload. So if you have a cluster of 100 or 1,000 machines, you can imagine that every change, like every new configuration that gets pushed out, or every time the membership changes, for that one change, there's going to be a lot of servers or processes that are interested in that change. Right? So you have a bunch of reads for every write that you do. So these are two things you want to take advantage of. Another thing we wanted was to have a general coordination kernel. For all those things, all the coordination primitives I listed earlier, you can kind of imagine in your mind what that primitive would look like, right? What a semaphore looks like. However, we found that when you go from application to application, they all have different twists on what happens. Like what happens with a lock. That when you take out a lock, does everybody know that the lock has been taken out by a given process, or only the lock holder? Is only the lock holder the one that knows? You have revocable locks, read-write locks. I mean, there's all sorts of variants for each of those coordination primitives. So we wanted to come up with a general kernel that we could use to implement all of those right at the client without having to modify the service. Of course, we wanted it to be reliable and easy to use. Okay, so there's, oh, yeah, go ahead.
So the menagerie of different kinds of locks out there, these are things that get put on by the application programmers.
Yeah, yeah.
And I'm wondering, is 90% of the reason why they come up with special lock primitives to get around some performance issue? Or are they...
Yeah, I think you're right. Yes, a lot of it is a performance issue. Because a lot of times they can make certain assumptions that make the locking problem easier. Or they can't. Yeah. Yes. Right, exactly. That's right. Okay, so there's three notions that we took, kind of design principles, to implement ZooKeeper. And the first is wait free. So one thing we wanted in a distributed environment, we wanted to avoid ever having two processes wait on each other. So if a fast process wants to do an operation in ZooKeeper, and there's a slow process out there, we never want the slow process to block the fast process. Now, this is with respect to ZooKeeper. There may be other reasons to block that. I mean, maybe the application is implementing a barrier or something, and it needs to block. But we don't want ZooKeeper to make that kind of blocking happen. So we want the ZooKeeper API to be wait-free, right? Now, one of the problems with this approach is that we have some primitives that are blocking, right? A barrier, by definition, is blocking, right? So we need to be able to implement these efficiently, which means we need to be able to efficiently wait for conditions, right? Yeah.
I'm just giving an example of what you mean about so-called cancel out hassles, because that's like the name of the game here, right? The whole point is what they know. So
Well,
I understand what you said.
right.
I'm trying to understand what's left in the space of
Well, let me give you an example. So, for example, if you're implementing a locking API, there are some out there. Let me go to the configuration. It's simpler, right? You have a configuration. You want to change the configuration, right? Now, a lot of the caching semantics or update semantics of file systems or things like Chubby even. When you make a change and you have processes watching for that change, the change doesn't actually happen until all the processes either acknowledge the change or are pronounced dead, right? So that might be desirable for some situations, right? But for other situations, you really want the change to get pushed out there and it to be propagated out as fast as it can, right? So you don't want to actually wait, right? You don't want to wait for the slow process before that write completes. Does that make sense? So now you may. Well, you do want coordination. So, but some of the coordination primitives are eventual, and some of them are. Some of the coordination primitives want consensus across all the processes, but some just want the kind of eventual consistency. So, like another one is leader election. So you can imagine some cases where a leader gets elected, and as soon as the system decides the leader is elected, that leader can move on. Now, other processes that are watching for a new leader to come on board, they can be delayed. They can find out about that later. They'll go to the old one, they'll find out he's dead. But meanwhile, you want the new leader to start working, right, and going on, right? And again, sometimes you don't want that, but oftentimes you do. And we found that usually you do. So, yeah. Okay? All right. Yeah, so the notion that sometimes you do want everybody to come to agreement, that's why we need to be able to support those applications, because there are times that you need that. Another thing we did was serializable versus linearizable. So being able to have linearizable changes is one of the requirements. We really want our system metadata, our system state to be consistent, right? So we want linearizable writes. However, reads are kind of eventually consistent. So we do this trade-off where writes are linearizable, but the reads are serializable. And we kind of tie these two things together with client FIFO ordering, right? So all the requests in ZooKeeper are from a given client are processed in order. All the writes are linearized from a client are linearized with all the other writes from all other clients. But reads are not, right? But they do have this, because a client can do a write and a read, there is some ordering constraints there. Okay? So this allows us to do stale reads, right? Yeah.
And the potential clients of this service, adding a little bit of weakness to this model, has that caused any problems for them?
You know what? So from our experience, no. And actually, normally they don't even think about it. Now, we did run into a couple of applications that found that if they could do a linearized read, they could avoid some overhead, right? Where they do a read, and then they start doing changes based on that read only to get an updated read. And if they could have done a linearized read before, they could avoid some extra processing. So we actually introduced a notion, which I'll show in the API, but you can actually do what we call a synchronization point and then do a read, which kind of converts a read into a linearized read, right.
It's like a memory barrier on this weekly order.
Yeah, right, yes, right. But generally that's not used. So generally the eventual is fine. Yeah.
Just to make sure I'm understanding, so can I rephrase what you say as you're providing session guarantees for the client?
I don't know. I'd have to. I mean, it's been a while since I've looked at Bayou and those guarantees, so I'm not really sure. Yeah. Would you answer yes to that? I don't know.
Well, I think, but I'm not necessarily sure I understand what you mean by serializable. So.
Oh, serialize. Right. Yeah. I'm sorry. I haven't read that word for a while. Okay. Okay. The third design aspect we have is change events. So we want to be able to allow the client to watch for changes, right? This is much like cached invalidations. And I should point out, my background is distributed storage systems. So when I look at problems, I see files. Yeah.
Can I go back one? You don't have to go back to the slide.
Sure.
So like Amazon has embraced an even weaker one.
Yes, right.
So I'm curious, when you guys thought about this, how did you decide, well, we're going to go this week but no weaker?
Well, so this is really everything we did was very much driven by application needs, right?
You're going to break a whole bunch of applications that you didn't get right away.
Right, exactly. Yeah. So one of the things So one of the reasons we need write order is because ZooKeeper is ground truth for many of our applications, right? If ZooKeeper is wrong, then everything breaks, right? So we need to make sure that ZooKeeper has correct information, which is why we have the
Amazon model was always that there was higher level reconciliation.
Yeah, exactly. Yeah, I mean, to be honest, like the Dynamo thing is quite cool. But I've always wondered if you can use it for anything besides checkout, right? I mean, because that does have this nice reconciliation. Yeah.
Real side effects, they ship I've had 2 copies of the same book that I ordered for Jeff that he got. And they just eat the copy.
Right.
To India.
Really?
But in exchange.
Yeah, agreed. Yeah, so, yeah. It's just as an aside, one interesting thing, we've had discussions about this. So, Yahoo, in some sense, is very, the applications we have are very, fuzzy. I mean, they're like unimportant. They're entertainment-oriented. People use it for fun. I mean, it's all free. Well, not all of it. Some of our services aren't free, but mostly people use free services. So in some sense, and then you compare that with things like the stock market, right? There's tons of money, and you have to get everything right. And everything has to reconcile. And so we're talking about the difficulties between these two. And with financial transactions, you really need good consistency because finance is involved. But for our stuff, but if you really think about it, for our stuff, if we're not consistent, the whole thing goes down. And then we make no money. We actually make money off these free services, right? And we make no money. Now, if you look at the stock market, at the end of the day, they do tons of reconciliation. It's just incredible how unreconciled they are, right? So even in financial transactions, there's all these outside reconciliations that you can do, whereas in the system infrastructure, doing some of those things isn't always possible, right?
Is that on the financial side, there are no external side effects before you settle at the end of the day. You can always move the money back.
Right.
And so,
At least for some people. Right. They spent it already. Yeah, agreed.
You can undo.
Well, and actually, this kind of out-of-band reconciliation is built into the system, right? So, yeah. Whereas, there are some things. We have operations people that are in charge of reconciling some of the errors that we have, right? But if it gets, because things happen so quickly in the infrastructure, that if it gets really bad, things go bad really fast, right? As we've seen, actually.
That's actually a really interesting topic because I actually switch the Samsung guys on this a lot. It's very interesting system model. The argument is we don't need any better. And so, again, I'm trying to understand what you're saying. Are you saying that you believe applications that actually need better? Or is it just sort of a software engineering decision that, we're going to put the guarantees to the low level, and Amazon's saying, no, we'll build these guarantees to the higher level, and you believe that at the end of the day, sort of the applications are
Well, no, I mean, I think they're really targeted for different things. I mean, okay, I don't work. I know very little about Amazon, right? But the Dynamo pitch has really been for checkout, things like checkout, kind of things where you can actually you have this reconciliation step kind of in process that you can do right before you actually submit the order. You verify your cart, right? And then I assume once the order is submitted, it's not Dynamo, but maybe so, but possibly not, right? So actually, I would not advocate ZooKeeper for managing checkout because if you can make some of these simplifying assumptions, it's good to do it, right? And so ZooKeeper would not be appropriate for. I mean, Dynamo is definitely much more appropriate for a checkout application than ZooKeeper, right? Now, as far as like infrastructure, which is where we're going, right? This is infrastructure coordination. Then I think the requirements are more strict, right? So that's, yeah. All right. Okay. So the third design point, change events. So the idea is that clients can request change events. So clients can do a read and say, hey, if this data that I just read ever changes, let me know, right? So this allows monitoring. And we have this timely notification. Now, it turns out that the change events are also eventual. The guarantee is eventual. So we don't want it, because of the blocking thing, we can't block the writes. But the changes do get ordered with respect to the writes and the reads. So they come after the writes, of course, and they don't block it. And then before a client ever sees the effect of the change, if he's interested in the change, he will see it, right, before he ever sees the effect. So that's kind of the ordering guarantee. So it's kind of loose. It's very loose, right? But the interesting thing is it works out really well. And as we'll see in just a second. So this was our hypothesis. When we designed the system, this is what we were trying to show, right? That by taking these three design aspects, by implementing these three design aspects, we can get coordination, right? So, yeah, go ahead.
Just so that I can stay grounded here,
Uh-huh.
I don't think that you would use this to update medical records because you would likely end up squashing somebody else's update.
Oh, no, because writes are linearizable so that we can't squash other people's updates. So that's actually why we have the linearizable writes. Yeah. So here's a case. If we take the medical records, which I don't work on, and it's only vague, but let me see if I can come up with something. Right. So if you have medical records, you can imagine two doctors that are using these medical records. I don't know. Maybe they're working on your problem. I don't know. But anyway, so the first doctor goes to update your medical record, and the second doctor goes to update your medical record. So what will happen is both doctors will initially pull down your medical record, right, and look at it, make a change. And then both doctors will do what we call a conditional update. So actually, it's on this. It's right here. So both doctors will do a get data on your medical record, right? And they'll get the data back along with this stat structure that has information about versioning, timestamps, that kind of thing, right? And then when both doctors go to update the data, they'll do a set data, and they'll have the new data here, and they'll put in the expected version, the version that they saw before. So one of those updates will succeed, and the other one will fail, because by the time it gets processed, and since writes are linearizable, the second one will fail because of a versioning error. Okay, so that's the linearizable updates. Now, on the other hand, you can imagine these two doctors working, right? And the first doctor, actually, it's kind of the same example, right? In the first one, these two doctors are working on it. They both do the read data, right? Oh, I'm sorry. Let me construct it a little bit differently. So the first doctor does the read data, right? And he gets it. He gets the medical record, and then he makes a change, right? And then he pushes the change up, right? Now, the second doctor comes in and does a read of that data, right? Now, even though the change is actually complete, he may get a stale version, right? Now, if he says, give me the data and I want to watch for changes, The guarantee is that even though he gets the stale data back, eventually he'll get notified that, hey, there's this change that's been made. Maybe before you even read it, right? But there's been this change, and you can see it now. So does that clarify a little bit? Good. Actually, it's good because, yeah.
So I have a question to you. Do you break out expected version as a non-opaque data structure? In other words, do you have any intention that the user might put something in other than what they got back when they copied the data?
For the expected, yeah. It really is mostly a token. Yeah, I mean, based on our implementation now, you can kind of predict the expected version number.
Like trading, getting expected versions from someone else and say, as long as it's more than
No, and the expected version is a equality, as you are pointing to. So it really is kind of opaque. I mean, it does have some order. It's monotonic. So the application programmer can assume monotonic, but they shouldn't assume other things.
Another way to ask questions. Should we think of this as a capability? In other words, are you trying to prevent me from writing data that I haven't read?
Well, it turns out that when you do a set data, you can always pass a -1 for the expected version, and then it'll go through. We won't do a version check. So you can always bypass it if you really want to. Right, yeah. Good. So I think I've covered the watch and the conditional updates. Yeah, so that's good. Let me, so I should just say, it's patterned after the file system API, right? We have create, delete. We have read and write. We have exist and ls, get children. One of the things to notice is coordination data is small. I mean, it's supposed to be small, right? This is data about coordination. So it's like coordination metadata. So it's really meant to store small pieces of data about coordination. It's not a data store. So there's no partial reads, partial writes, so there's no seek. Because there's no seek, partial reads, partial writes, we don't even do open or close, right? So every time you do something, it's just with the full path. Now, the data model, as I said, is like a file system. One thing that's a little bit different is, so we call these, this is a tree, and the nodes in the tree we call Z nodes, or ZooKeeper nodes. Turns out, node is a very ambiguous term. It's horribly ambiguous. So we always use the term Z. So each Z node can have children, and it can have data. So it's kind of like each Z node is a file and a directory. Okay. Now, when we create a Z node, there's two flags we can use. One is an ephemeral flag. And when a client creates a Z node with an ephemeral flag, it's telling the system that if the system ever detects that the creator has failed or has died or has gone away, that the node should be deleted. Okay? And the other one is a sequence flag. And this says, take this path that I give you and append a monotonically increasing suffix, a counter to it. So you can see here, you can imagine here's two ephemeral nodes. So the worker 1, when it comes up, it creates an ephemeral node, and it appears here under the worker's Z node. And if this worker 1 were to ever die, then it would just automatically disappear. It gets deleted. And here, actually, I'll show you an example of sequence numbers. But here, the client created a file called s-. That was the file name. And it specified a sequence number, so it had 1. So a 1 got appended to it. And thus we come up with s-1. Sorry. Ugh. So, sorry about this. Okay. So if you look in the API, this is why in the API create returns a string. Because if you use the sequence number flag on the create, then you're going to get a different path name than you've specified when you did the create. So let me just show you how we use this API to implement some of the coordination primitives I talked about. So one of the easiest ones is configuration. It's easiest, and it's super important. Right? So this gets used a lot. So when a worker comes up, it needs to get the configuration data. So there's going to be some path in ZooKeeper to the Z node that holds that configuration data. So the worker will come up, it will do a get data on that path, and it will specify true for the watch flag. So it wants to know if this data ever changes. So the get data will complete, it will have the configuration, it'll start working, start running with that configuration. And then later at some point, an administrator wants to change the configuration. So they'll do a set data with this new configuration. Here we just say -1, so they're bypassing version checks. And once this set data completes, all the workers are going to get this event saying, hey, settings has changed, right? So the workers will then issue another get data, again with the true, and get the update, right? So it's very simple, right? So that's configuration. If we look at group membership, it's also a very simple thing to do. A worker, when it comes up, it's going to create an ephemeral Z node under a workers directory, and it's going to use its name. So whatever the name of the worker is. And maybe some sort of information about it, like maybe it's host and contact information, rendezvous. So it'll just create that, and then it's kind of like fire and forget, right? It just does it at the beginning, and then it just waits till it dies, and then this Z node will get cleaned up automatically. Now, at any time, if we want to know which other processes are alive, we just list children on workers, and we can see who's alive, right? Does that make sense? So that's another. This is an easy, a simple way of implementing group membership with the ephemeral flag. Now, a slightly more complicated one is leader election. And the approach we're using here is locked files, right? So on a normal file system, it's very common to use this lock file method for doing locking. And usually with lock files, you check the lock file. So here we're going to specify a leader Z node. And we're going to do a get data on leader. And if it exists, then there is a leader, and we'll follow it, right? We'll use the information that we get back, and we'll follow the leader, right? So we exit. Now, if there isn't a leader Z node, then we're going to try and create one. Now, if you can imagine if there's two processes that are executing these kind of concurrently, the two processes first call get data. They see there's no leader, so they'll come here and they'll execute this create. So one process will be able to create the node. The second process will fail because the node will already be created, right? Because again, creates are linearizable. So one process is going to become the leader. We're using this ephemeral flag so that if that process ever dies, this Z node will go away, and we can restart the leader election. So if we successfully create, then we start leading, we exit. Otherwise, we go to step 1, and we see who the leader is, right? We tried to become the leader, we failed, so there must be another leader. Right? Yeah? It's an election. So it has a race, but we resolve it, right? Yes. Oh, yeah. I see what you mean. Yeah. So, okay, this is a funny thing. So, with leader election, when I first started working on this problem, years ago, I always thought leader election was about picking the best leader. And, that's really hard. So a lot of times we satisfy ourselves with picking a leader, right? Picking anyone. So, like in Florida, right? Remember the election in Florida? We just wanted to get a president. We didn't really care which was the right one. No, but I'm joking a little bit here. But yeah, you're right. In this leader election algorithm, we're assuming that each of the processes are equally worthy of becoming a leader, right? And so it's basically whoever wins, right? Which is what you're pointing out. Yeah. So if you want to do something more sophisticated, then you would have to have a more sophisticated recipe. But oftentimes, it's very common that where you have this need of just picking a single leader, and just as long as you get one, then you're good, right? And that's what this is aiming for. Now this works. We use this in practice, and it's really quite good. There is one problem with it, and that's when the number of processes involved with leader election gets large, right? So you can imagine if you have 2 or 3, then this is great. But if you have 100 or 1,000, it's a little bit more problematic, right? Because, I'm sorry, I missed the last step. Right, so it turns out all the followers to a leader, right, they've all done the get data with this true flag, this watch flag equal to true. And the reason we do that is because if the leader ever fails, we want to rerun leader election. So when the watch is triggered saying, hey, leader went away, the followers are all going to restart the leader election process so they can re-elect the leader amongst themselves, right? Now, one of the problems with that is if you have 100 or 1,000 processes, you're going to wake up all these processes just so you can pick one, right? So you have this herd effect, which is bad. So if you want to avoid the herd effect, you can use this other protocol. Now, for lack of time, I'll just point out a couple of aspects about it, and then you can work through it on your own. But the basic approach is that each of the processes that start this, so I'm casting this in terms of locks, right? But you can also use it for leader election. So the idea is that each process that wants to acquire a lock or wants to become a leader starts, and that process creates a Z node under a certain Z node, under a locks Z node, right? And because they use the ephemeral flag, if they ever die, their lock will get released, and they use the sequence flag to establish an ordering. So when all these processes come in and start creating these Z nodes, they're going to look like this, where we have X dash, because we're doing create with the X dash, and then they'll have the sequence number appended to them, because we're using the sequence flag. And this establishes an ordering. And once we have this ordering, to figure out who's the leader or who's the lock holder, we simply have to look at who has the lowest suffix in this list, right? And whoever has that is the leader or the lock holder, right? And so that's what we're doing here. And the other key, the way we avoid the herd effect is that when we're waiting to become leader or waiting to acquire the lock, we only have to watch the node in front of us. So in this example, the process that created X11 is the lock holder, right? Now, the process that created X19 has to wait for this process to go away to become the leader or to hold the lock. Now, X20 actually has to wait for X19. He can care less about X11, right? So we have each of the processes waiting on one other process, one other Z node. So when a lock gets released or a leader goes away, only one process will be woken up, and that will be the process that will become the leader. Okay?
Your worst case failure scenario is the next guy in this chain you thought was the one who's failed.
The worst case is that the what do you mean?
So in other words, that the guy, who's next to the head of the line, for the next person to wait for it, that they're the one that dies after they get the lock. And then the next person gets the lock.
Oh, before they actually use the lock. Is that what you're saying? Yes, that's right. That is the worst case. Right. But, that case, with a slight timing thing, they might get the lock, start doing something and fail. And then it's still worst case, right? Because they haven't really done anything. Yeah, so, it turns out one, in some sense, the worst case is when these intermediate ones fail. So, like, for example, if X19 fails, X20 will wake up, right? And he won't be the leader, right? So he'll run it again, and he'll realize he has to wait on X11. So he'll wake up, and then he'll have to wait on X11. Even though he's not, so he's going to wake up even though he can't acquire the lock, right? So. Okay, so this is lock. Now, it turns out we can do a slight tweak on this. So this gives us exclusive lock. Oh, and I should point out, one of the reasons we started working on this is because we had developed ZooKeeper, and we had a bunch of people using it. And we had one of the application developers come back to us and say, the ZooKeeper thing, great, we love it, fulfills all our needs, but we need read-write locks. We have to have read-write locks. Just at this one little point here, we have to have it. And so we looked at putting read-write locks into the API, right? And it turns out that would have broken a lot of simplifications of the implementation. Once we have read-write locks in our processing pipeline, now we have to delay operations based on other operations that are in progress or based on other clients. This wait-free thing gives us allows us to simplify our implementation a lot. And so it like broke our system to put it in. And we were really frustrated. And then one day, driving home from skiing, that's why you need to go skiing, I came upon this way of doing read-write locks with just the API that we have. So this is the exclusive lock, right? Now, it turns out you can do a slight modification on this to do read-write locks. Now, I won't go into the details, but the key is we do everything the same. And the previous exclusive lock works exactly the same. The only difference is that in step 4, when we check for existence. So the criteria for holding a read lock is just to make sure that there's no exclusive locks in front of you. Right? So if you look at the list and there's no exclusive locks, then you hold the read lock, right? And this actually gives you fair read-write locks. So, but I'll leave that as an exercise. Let me just talk a little bit about how ZooKeeper looks internally. As I said, the coordination metadata is very small, and with our API, we require it to be small. You can only do full reads and full writes. And not only that, in our implementation, we have this sanity check that says if you ever try and read or write more than 1 meg worth of data, then you fail, right? And that means you're insane. So if you do 100K or 900K, you're still insane, but you'll pass the sanity check, right? So this is really targeted for coordination data on the order of kilobytes or maybe tens of kilobytes, right? So because the metadata is so small, we can keep all the data in memory. And this allows us to simplify our implementation, and it also allows us to have very consistent latencies, to have very consistent performance, because we never have to worry about swapping to disk, right? In order to do the linearizability for changes, when these servers come up, they're going to elect, now this is internally, so this is a different leader election. They're going to elect a leader amongst themselves. And that leader is going to coordinate all changes to ZooKeeper. So any change requests from what we call followers, the servers that aren't the leader, will get forwarded to this leader. That leader will apply the change and will push it out using atomic broadcast to the other servers, the other ZooKeeper servers. And the atomic broadcast algorithm we use uses quorums. And we actually have a flexible quorum system, but usually people use majority quorums. Okay? So this is kind of what the full system looks like. You have a server. So this server in the middle got elected the leader. The clients connect to any server they want. We use random load balancing. So clients will randomly connect to servers. An option, if you have more than 3 servers, one of the options we turn on is that the leader doesn't accept client connections, which is why there's no line from clients to this server. But clients will then send requests to these servers. If it's a read request, the request will be served out of the local copy of the state of the server. If it's a write request, it'll get forwarded onto the leader and then get executed using the atomic broadcast. So once the leader executes the request, broadcasts the resulting state change to the server server will apply it to itself and will send the response back to the client. The local servers, the server that the client is connected to, also is in charge of tracking watches for doing our watch events and for checking the liveliness of the client. So it helps detect. It suggests to the leader who may be dead, and the leader is the one that actually decides which clients are alive and which are dead. Okay, so let me just show you a quick evaluation to some of our performance numbers. This is on we have a group cluster of 50 machines. They're kind of old now, but they're dual-core Xeons with 4 gig of RAM and 2 disks. Actually, the 2 disks is actually important, but I don't have time to talk about it. That's why I mentioned it. But so one of the things that we do, we talked about how the state is kept the state is replicated across all the ZooKeeper servers and is kept in memory. But we have durability requirements. And specifically, one of the things we want to deal with is simultaneous failures, usually a power outage. So if you have a power outage, then all your machines are going to go down, and we want to be able to recover our state. So to do that, we use the write-ahead log. So whenever there's a change at a server, we send it to our atomic messaging system, our atomic broadcast system, does a write-ahead log for the messages that get broadcast. And so that way we can recover from things like correlated power outages. So we did a test of our atomic broadcast just to see what these choices mean. So it turns out if we remove that option, if we made it so that all we did was in memory, everything was in memory, we get pretty low latencies. This is on the order of 2 to 3 milliseconds. This 2 milliseconds, and basically if we also do the write-ahead log to the disk, it comes out to be 4 milliseconds. But it turns out disks cheat as well. So disks actually have a write-ahead cache. So oftentimes when you say flush and you send it to the disk, sync, I'm sorry. When you say sync, sync gets it to the disk, but the disk may not put it on its platter. So if you have a power outage, it may not be there when you come back up, which kind of defeats the purpose of sync, but never mind. So one way to do that is you turn off the write cache of the disk. And if you do, then your latencies increase a lot. So one of the things we're working on right now is kind of bringing down these latencies. What tricks we can do to bring this down, we're studying exactly how much you really lose from the write cache when power outages happen. And this number here is still quite large, and we're looking into why that is. We use TCP between all our servers, and the latencies between our servers are like 20 microseconds, so it shouldn't be this high.
So is there a sort of a reason why the latencies are not monotonic, or is there
Oh, you mean right here, this one?
No, well, I was looking at the net plus disk, and sort of I would expect latencies to go monotonically up if it's 3 servers.
Oh, yeah. Yeah, not really. Until you get, yeah, it doesn't really, because the request completes when a majority has it, not all of the servers, then it really just gets balanced out. You add more servers. As you add more servers, you get more heads. So in theory, your latency could go down because you have more heads, but we also require more for a majority, and so it kind of balances it out. That's why it's relatively flat. Now, it does change a little bit if our throughput, well, it changes quite a bit if our throughput goes up, because then you start getting queuing delays. So one of the things that we have right now is, so in that picture I showed, it was quite accurate, the picture where the leader broadcasts the change to all the other servers. And because of that, as you add more servers, the leader needs to broadcast to more servers, and its NIC gets saturated. Its network interface card gets saturated. So we're using 1 gigabit Ethernet cards. And so because of that, this is the graph of a saturated system. So so basically we have, I think, 900 clients just pounding on a cluster, right? And then we just vary the cluster size. We vary the cluster size with these lines, and we vary the percentage of read requests. So 0% is all writes. So you're doing all writes. This really shows you the throughput of the atomic broadcast layer. And then as you go to 100% writes, then you're not going through the leader. Everything's coming out of local cache, and it goes way up. Actually, right here, it's perfectly scalable. As you add more servers, your throughput goes up because servers don't need to communicate with each other to serve requests. But down here, the leader has to coordinate every request. So the leader becomes a bottleneck here. And because of the leaders doing this and the network card is getting saturated, as we add more servers, the throughput goes down, right? So if, obviously, that can cause queuing delays and thus increase your latency. One of the things we're looking at here is we'd like to change the servers for at least the data transfer to use something like chain replication. However, there's there's a pretty big impact on our implementation to do chain replication. One of the things we do is we combine. So we also have to do failure detecting, right? It's kind of funny that the system that we provide to do group membership and leader election and failure detection also has to do that itself, right? I guess it's logical, but anyway. So in our system, we have to do failure detection, and currently we use the same channel to do broadcast the data and to do failure detection as well. And so, so converting to chain replication would make that a little bit more complicated. Now, this graph here on the right shows what happens if all the requests go to a leader. So this graph here shows the importance of the choice we made to have, basically, to support stale reads, right? Because we support stale reads, our performance can go way up. Oh, I should mention, I mean, this is really the target workload we have here, right? Where there's like 10 to 1 reads to writes, or even 100 to 1 reads to writes. So this is really where we're targeting, and we get spectacular performance there. Now, if you were to send everything, so all requests had to go to the leader, then you would get strong reads. So you'd get linearizable reads. The performance does really suffer. So all right, so I'm out of time. Let me just show you. This is a workload, a trace that we took from one of our large. It's our fetching service from our crawler. This is the activity. So the red lines indicate reads. The black lines indicate writes. You can kind of see our target workload really does have this read-dominant characteristic. And you can also see that the number of operations per second, even though the fetching service uses ZooKeeper extensively, is very much below our saturation point. So we're quite happy with the performance. So it's been used a lot at Yahoo. We use it for cross-colo locks. Even some of the things you see on the front page is coordinated with ZooKeeper. So yeah, it's used a lot. Let's see. I will skip this part. So just in summary, the goals that we found that it is easy to use. We've had really good reports from our users that have come back and said, we were able to build the system much quicker than we otherwise would have because we were able to use ZooKeeper. I should point out, there are some caveats to the easy-to-use thing. So the idea with ZooKeeper was really to present the distributed coordination problem in a way that the users can deal with, right? They still have to deal with the problem. They have to deal with the failures, and they have to deal with the changes. And although we've made it a lot easier and we've helped things a lot, there still are some corner cases that need to be addressed. But on the whole, we're very happy with the easy-to-use story. The performance is great. It's been very general. We haven't had to change the API to accommodate new requests. It's been very reliable. It's an open source project. We're on 3.3 on Apache. This is the URL. There's plenty of open issues and things to do, performance improvements to be made. Hopefully you guys know about open source. It's great. To be honest, I wish I had this when I was a student because it really allows you to distinguish yourself. When you go to employer and you're right out of school, sometimes you don't have a lot of stuff to put on your resume. But being able to put, I'm not just talking about ZooKeeper, just in general. This is just a pitch for open source in general. If you can put that you really worked on something that somebody uses, especially if the person interviewing you uses that thing, it's a very powerful thing. So I certainly, take a look at ZooKeeper. We'd love to have the help. We actually had like 3 Google Summer of Code students that worked on some new things for ZooKeeper. But yeah, so anyway, and we also have the committers, the managers of the project, are both from Yahoo and Cloudera, and we're always looking for more people as well. So thanks. Yeah.
Can you give us some sense of how many production properties make this?
You know what? It's really funny. Not really. So it's. Because
you don't know.
We don't know. You know what? We don't know because a lot of people just pick it up and go with it. I mean, even inside of Yahoo. Inside of Yahoo, just really quick, I got this call at my desk, and I get this call, and they're like, hey, yeah, we're working on Keystone, this new advertising thing. We just went live today, and we're having our queues back up, and they're seeing all this stuff that I don't know what they're talking about. I'm like, what? And they're like, yeah, we think it's ZooKeeper. And I'm like, okay. I mean, I'd never heard of them. I didn't know they were using our stuff, right? And so they start talking, and I realized, I'm like, this really sounds like split brain. Are you sure you tested this? I kept asking over, did you test this? Oh, yeah, we tested. And so I'm like, yeah, can I look at it? So I logged on, I looked at their cluster. And they had 3 ZooKeeper servers for fault tolerance, but they were all configured to be standalone. Right? So we had 3 standalone ones, but the clients were configured to use them as a cluster, right? And I'm like, oh, wait, wow. And they're, oh, yeah, in testing, we always tested with standalone ZooKeeper. But when we went into production, we wanted to make sure that we could handle faults. So, yeah, so that was very tragic. And actually, one of the slides I missed, I skipped over, is I think there's a lot of really interesting work in terms of, for these reliable systems, in terms of validating assumptions. Because a lot of times in the protocols we come up with, they rely on assumptions that seem very reasonable to us, but don't always happen in practice. And actually, as I've looked deeper into root causes, I realized a lot of them we could validate and really, and I think that would be a great piece of work. But, yeah.
For the ones that you're aware of,
Mm-hmm.
people normally just run with a few servers?
Yeah, so usually it's, yeah. Uh-huh.
If people use more than 3 servers,
Yeah. Uh-huh.
are they doing it because they want to mask more players or because they just need to scale out?
Both. Yeah, so it's both. Sometimes they use it. So one thing, they usually try and do 5. And the reason they do 5 is because if they want to take a server out for maintenance, they want to be able to still handle another failure. So 5 is kind of a good number. Once you get past 5, usually they're doing that to scale reads. So, or to really handle more failures. Like for our fetching service for the crawler is very important. And I think they went to either 7 or 9, partly because they have thousands of clients, and partly because they just don't want it to fail. Right? So, all right, great. Yeah.
So 7 or 9 is a big number from sort of consensus point of view, but from like Facebook, that's laughable. So I'm just curious, have you had properties where people have then put another caching layer in front of your clients?
No,
So
we.
you're really seeing all the reads you think. I mean, obviously you
Yeah.
know.
Uh-huh.
But you really believe that everybody who's using yours is actually pushing all the reads to a server and not
Yeah.
absorbing caching.
Yeah. So really, I mean, we actually introduced something called observers, which are proxies, but it's not really used. And usually, the proxies are used to avoid latencies, to like move servers, move the data closer, like cross-colo, rather than removing load. So so it turns out that because, in some sense, we expose caching through these watch events, that kind of exposes the caching up to the application, right? But yeah, our performance, I mean, especially with respect to reads, is way higher than we've needed. So we haven't had any issues like that. And yeah. So I mean, the clusters, we have enormous clusters using 3 to 5 ZooKeeper clusters, and they're not. It's not a problem. Part of it too is the nature of the data. So usually, so usually on a system, it could be enormous that is good. I mean, there's no faults. There's nothing happening. There's no activity on ZooKeeper, right? So because of the way it's used, there's just not. Actually, the reason we need the performance is to handle the bursts. So when there's a big configuration change, when there's a massive failure, when there's an upgrade or something going on, then that's why we need the performance to handle the burst. In the normal case, there's really not a lot of things happening with ZooKeeper.
One of the possible stories Ken Berman was talking about is how Amazon blew up because of their reliable multicaching.
Yeah.
Have you guys sort of spec'd out how ZooKeeper will melt down or when it will melt down in terms of
So it melts down. Yeah. Yeah, so there is one problem. Yeah, so we avoid some of the multicast things. Multicast has some inherent issues, right? And so because we use TCP, we avoid a lot of those. Actually, there was this work by Ken Student. I should know his name. I'm sorry. RX Multicast, or Dr. Multicast, whatever. Where he kind of outlines some of those issues. And for those issues, the ops guys hate it when we use multicast. So it's kind of a forbidden technology at Yahoo, which is kind of sad. But anyway, yeah, so we don't really have those issues. The real issue that we have is the write scaling issue. The way it's architected right now, if our write load, I mean, once we hit that, it doesn't go. There's no, there's nothing you can do. Adding more servers only makes it worse. So yeah, so that's really the biggest problem. So that's why one of the pieces of work we want to do is the partition namespace, to be able to partition the namespace. There's two reasons why we haven't spent a lot of the time on it. One is our performance right now, I mean, even when you start combining applications together, is just so much higher than what they need that they can't have it. Now, we keep pointing out to them, you're going to grow, and so eventually you hit it. But yeah, we have a lot of headroom there. And the other one is that namespace partitioning, they can kind of do themselves if they wanted to. I mean, it's a little bit out of complexity for them, but they can use different ZooKeeper clusters to partition. Okay?
All right.
All right, great. Thank you.